Hi, I'm Alistair, and in this video I'm going to describe how you can use USB peripherals in your Arduino projects. Specifically, I'm going to show you how you can use an Arduino to read input from a USB human interface device, or HID, like any of these. Now, HID is a subcategory of device defined by the USB standard, and it includes common input devices like a keyboard or joysticks and joypads, as well as slightly more exotic peripherals like Magstripe readers or barcode scanners. Now, to use any of these peripherals with a PC is pretty straightforward. You just plug them into a spare USB socket, they'll get automatically detected by the operating system, and generally speaking they'll just start working. But if you want to use them with a microcontroller like an ESP32 or an Arduino, it's a little bit more tricky. Even though this Arduino has a USB socket here, that only allows it to be used as a USB slave device, which is how you upload code to the board from the Arduino IDE. But you can't plug a mouse into that socket, for example. To make the Arduino act as a USB host that can communicate with these sorts of devices, you'll need to add some additional hardware, such as this USB host shield. Now, this shield is based around the Maxim 3421 chip, which has an SPI interface that you can use with any 3.3 volt or 5 volt logic microcontroller. Now, you'll also need to write some code to make the shield interface with the input device and to interpret the data it receives from it. Now, fortunately, much of the core interface is the same for every HID device, and there is a library available that provides much of the base code for you. So you can just deal with the specific implementation of the peripheral you're using and how you want to interpret and act upon the data received. So let me give you one in-depth example, which is how to take the input from this USB barcode scanner and display it on this VFD screen. And why have I chosen this? Well, because you all know I love escape rooms, and this setup essentially functions as a decoder. Players can scan the barcode or the QR code on any item, and the display will present the number or the string which that pattern encodes. Now, there's loads of free tools and websites you can use to create barcodes and QR codes. You can then print the code out and attach it to any document or object. So here I've just gone to the first site Google gave me. I've chosen the sort of code I want to create, the message I want it to contain, and it has given me this QR code here. And if I scan that, you'll see that I get the output displayed over here. Now, this value is received by the Arduino, so you could then use it in any additional logic you want. You could require players to scan a particular object or a sequence of objects. But for this example, I'm just going to display the decoded value on this display, which is a cute little display that I thought was thematically appropriate to using a barcode scanner, as if you were pretending to work on the checkout at a shop. Now let me show you the components I'm using. So the easiest way to make a microcontroller operate as a USB hub is to use one of these shields. Now, they come in a form factor that's designed to simply slot onto an Arduino Uno or Mega, and that's definitely the easiest solution. It makes all of the necessary connections to power the board, to create the SPI interface to the onboard USB chip, and also it exposes all of the GPIO pins from the Arduino through these additional header pins, so you can still connect any other devices to the unused pins. Now, even though it's designed for an Arduino Uno, you can connect one of these shields to another microprocessor instead by wiring to the appropriate pins. It uses an IC-SP connector on the bottom here to provide 5 volts, ground, clock, MISO, MOSI and reset lines. And additionally, it normally uses the pins that go to the Arduino's GPIO pin 10 as a slave select line, pin 8 is an interrupt line, and pin 7 is a general purpose pin. But you can route those to other pins by attaching wires into these 3 exposed terminals on the board here. Now there's also these little solder bridge connections here, and you need to put a blob of solder between the appropriate pads to specify whether you want to use this with a 5 volt or a 3.3 volt device. Now if you are using a 3.3 volt device, you can also get a different style of USB host module like this one. Now these only operate at 3.3 volts. Again, you'll have to wire to the SPI interface using the pins that are indicated on the base there, as well as to reset, interrupt, ground and power. And that brings me on to the subject of power. So USB devices need to be powered, and when you plug your HID peripheral into this port on the USB host shield, that provides an interface both to send and receive data, but also to supply power to the device. Now that power in turn is supplied via the connection to the Arduino underneath it. But the components on the USB host shield themselves also need to be powered, as does the Arduino and any other components you might have plugged in, like that display I was using earlier. And combined together, all of those devices can simply require too much power than the poor Arduino linear regulator is able to supply. So one way to deal with this is to inject power into the USB peripheral separately using a USB powered hub like this one. So what you do here is you plug the hub into your USB host shield like this, and then you plug your device into the hub. And now data is still being passed back from your peripheral through the hub to the Arduino, but the power is being injected by a separate DC power supply here. Obviously this does need to be a powered hub. It's no good using an unpowered hub. That would simply provide even more drain on the device. Now the other advantage of introducing a hub is that it also gives you the ability to connect multiple USB devices to the shield. And you absolutely can do this. The hardware and the software library I'm using both support it. However, I would not recommend it, since it makes your code significantly more complicated and prone to error. With each additional type of USB device you add, you have to route the incoming data to the appropriate parser to handle the data from the device that sent it, and that can quickly get pretty messy. I'll explain more about parsers in a moment, but I recommend building this project to support one specific device, but you can still use the powered hub as an intermediary to supply power to that device. And here's a diagram just to illustrate that wiring. Now let's go on to look at the code that's running on the Arduino. So I start at the top with some external libraries which I'm including, and the library I'm using for interfacing with the USB host shield you can download from this GitHub link. You can also install it directly from the Arduino IDE manager. If you search for USB host, it is this library here, USB host shield library 2.0. Although it's actually version 1.6.2 at the moment, so that's a little bit confusing. But that's the library I'm using here. And this actually has several different header files that we need to include. We always include the general purpose HID, the HID universal device, and the boot device libraries. This header file here, you only need to include this one if you are using a powered hub between the host shield and the USB peripheral you're using. So as I demonstrated, that's a good way of injecting additional power supply to the USB device. If you're using a low powered peripheral, you might be fine just plugging it straight into the host shield, in which case you don't need to include this line. But if you are using a hub, just put this in as well. And this final library, this is one that I wrote just to interface with the particular VFD display I'm using. Now this was the display I just happened to pick up off eBay secondhand, so it's fairly unlikely you're using the same display as me. If you're using an OLED display or an LCD or something like that, you would need to incorporate the appropriate library for that display instead. Then we get on to the constants section, and you see that I've got several arrays of character values here. Now to understand why these are here, this is going to take a little bit more explanation about the way in which USB data is transferred. So I've often used serial connections between devices which send a stream of data 1 byte at a time. And if you're transferring a text string, each one of those bytes generally corresponds to a single character in the text message. And the byte value is based on the ASCII code lookup table. Now, with USB data, it's a bit different because we're not transferring text or number data. Rather, we're transferring the state of an input device. And USB does this using a report format, basically a packet of data instead of a single value. And that packet of data might be structured slightly differently depending on the sort of input device it describes. So once we've received a report from USB device, we need to pass that information we need out from it. So our barcode scanner actually behaves almost exactly the same way as a USB keyboard. It scans a code and then it sends the decoded value as if it had been typed out. So you might think, oh, that's fine, we can just build up the character string of the barcode 1 letter at a time, just as we would read any other character data. But when you look at a keyboard, you realise there's plenty of characters you actually can't send in a single keystroke. To type an ampersand, for example, you have to press the Shift key down and the 7 key at the same time. The plus and the equals share the same key, as do the semicolon and the colon and many other symbols. And when you type any letter key, you can either get the lowercase or the uppercase version of that letter, depending on whether you had previously pressed the caps lock button, and whether you were also holding down either the left shift or the right shift at the same time. And there's also lots of variations of keyboard layouts. So the report received from a USB keyboard doesn't actually tell you what character was sent. The USB HID code for a capital M and a lowercase m are exactly the same because it describes the key or the combination of keys that were pressed, and it's up to you to determine how to handle that in your code. So these arrays, which I've put at the top of the code here, are the first part of how we'll do that. They define the special characters and symbols that can be obtained when a particular set of keys are pressed in combination with a modifier key. And that's going to be how our barcode reader will report those symbols. So this array here, this is what you get when you press the Shift modifier together with a number key. Here we've got the symbol keys when they are pressed with a high modifier and without one, so the high and the low value on those keys. And these are the symbols you obtain from one of the numpad keys. Now I've stored them all in progmem arrays so that they're not using up the allocation of space that we're using for the code here, because these are just going to be constant references that we'll look up into in a moment. Okay, so now we actually have to define an instance of a parser class that we're going to use that is going to make use of these arrays in a moment when we receive one of these reports of HID data. It's going to have 2 functions in it. It's going to have a public function which is going to be called parse, and this is going to take a reference to the HID device that sent the report itself, the length, and a pointer to a character array containing the content of the report itself. And then we'll also have another method here which we'll call key to ASCII, and that is what we're going to use to convert the keystrokes that the report contained into an ASCII character, and that's going to make use of these arrays up here along with some other logic that we'll look at in a moment. Okay, then we get on to a section of global variables. So these are variables that are shared between all the functions of the code. We'll initialize an instance of the USB host class, and we will also initialize an instance of the hub based on that USB host. Again, this is only necessary if you are using a powered hub to inject power. So the inclusion of the library at the top here, and also the creation of this instance of the hub class that are only necessary if you're using a hub. But I would probably recommend that if you can, certainly if you encounter any issues with erratic behavior or the board resetting when you try to use your USB device. That's a sign of it not being able to supply enough power. So that's generally a good idea to use a powered hub there. This is the instance of our HID device class itself, and we're going to create a universal HID device that we'll just call HID. And we'll also create an instance of the barcode parser class. So we define this up here. We haven't actually said what it's going to do yet, but we're going to create an instance of it which we'll call barcode parser. And then I've got two other global variables here. This first one here keeps track of the last character we decoded using our barcode parser from the report received from the device. And this is initialized as the delimiting character you get at the end of a text string. This is essentially because barcodes and QR codes can come in lots of different lengths, and we need to know when we've received the end of scanning one code and before we begin scanning the next. So we're going to keep track of what the last character received was. If it was a string terminating character, like a line break or a character return or something like that, we'll know that the next character received after that will be the start of the next code being scanned. And then I initialize an instance of the display, my VFD display, which I included the library of up here, and we're going to use that to send the output to the display by simply writing messages to this. Okay, so this is where we actually get onto the meaty bit of the code, which is where we apply the logic of how we interpret this incoming USB report of data sent from the HID device, which is the barcode scanner in this case. So what we're going to do is we're going to look at different elements of the buffer that's been supplied, and we're going to use that to kind of decode the information we want to receive from it. And the first thing we want to do is to check whether we've actually got some valid data to pass. Now there is an error byte that can be sent in that buffer. If the second element of the buffer is equal to 1, that means there's been an error encountered, a key rollover error. And if that is a 0, that means there's actually nothing in the buffer. So in either of those two cases, if we've either got an error or an empty report, we'll simply return back out of this function. There's nothing more for us to do. Assuming that neither of those two cases happened, what we'll then do is we'll loop over the next bytes in the report, and what we'll do is if any of those are 0, we'll skip over them onto the next one. Then if they're not 0, so we've got a non-zero value, we need to know if the byte we're looking at the moment is the beginning of a new code being scanned or whether it's just the continuing value from the previous one. So to do that, we'll look at what the last character received was. Remember that this was initialized to this null byte value anyway, so if it's already that, it means either we've just started the code or that was the last thing it's been set to. So we're beginning a new code. We'll move to the beginning of the display, we'll clear any value that was previously sent to the display, and we'll also, for the benefit of debugging, we'll just print a blank line onto the serial monitor. If the current value that's being read in the buffer is equal to an enter key, that's when we'll set the last character value equal to this terminating byte. So that means that we know for next time we can enter this section here. So all of this section here, this is just managing the fact that we can be scanning multiple codes in succession. We need some way to delimit when one ends and the next one begins, and we do that by keeping track of the last character received. So that's what these two functions do. So then we fall into this section here. So this is essentially all of the actual data that we want to process. We have not got an error code, we've not got a blank report, we've not just got 0 data, and we haven't got a special value to denote that the previous scan had ended. This entire section here is dealing with the actual content of the data that we want to process. So in the case of the barcode, it's the numbers, or the QR code, it's the content that that code contains. And what we need to do is we need to convert it from this report format that we've received into an ASCII key that we recognize so that we can build up the display that we want to show to players. So to do that, what we need to do is we're calling this key to ASCII function, and we send that the first element from the buffer that was received in the HID report, and also the current element in the buffer that we're looking at as we loop through it. The reason why we send the first element separately is because this is where the modifier keys are expressed. So if an Alt or a Shift or a Control key is sent, that is always going to be contained in this first element of the buffer, in combination with any other keys that might have been sent as you loop through the report. Okay, so we'll send them both to key to ASCII, and we'll use that to turn it into a letter. And we do so in this function here, according to the specification, which you can view at this link here. So first of all, we need to tell, well, was a modifier key being pressed in that first byte that we sent to the report? And particularly, we only want to know actually if the left shift or the right shift key were being pressed as modifiers. So we do that by doing a bit mask of the modifier value that was sent in that first byte, and this bit mask here is a binary value which can set zeros or ones at different positions to represent different modifier keys on the keyboard. Here we want to know if either the left shift or the right shift was being pressed, so we will do a bitwise AND with the modifier that we sent to see whether either shift or both shifts were being pressed. And with that knowledge, we can now go on to process all of the other keys that we might have received. So the simplest case is that it was a letter. Now the letter keys are defined in the USB spec as between this byte and this byte. So this will give us an index into the key that was received, and then we add that on to either the uppercase alphabet in the ASCII code if the shift key was being pressed, or else the lowercase alphabet if it wasn't, and that will give us a character back that is of the matching case and of the matching position through the alphabet. Okay. The next situation is possibly a keyboard number was being pressed. Now these are the next batch of data items that could be said in the HID reports. So the key here ends at the hexadecimal code 1D. We then look at 1E for the numbers. And then what we do is if the shift key was being pressed, that means that we're trying to be sent the symbol that appears above the corresponding number. And we define that in this numKeys array at the top here. So these are the symbols that appear above the keyboard keys 1, 2, 3, 4, 5, 6, 7, 8, 9 and 0. So if the shift key was being pressed and a keyboard number was sent, we want to read from the program memory, from progmem, the value from the number keys array that corresponds to the index of the number key being pressed. If the shift key wasn't being sent in this report at the same time, we just return the key itself. But the problem is that the 0 key is actually a special case because number keys go 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. The 0 is at the end. So if it's a 0, we'll explicitly return a character 0. Otherwise, we begin counting from 1, which of the other number keys. So all of these functions here may seem sort of fairly obtuse, and they are a little bit, but what we're really doing is we're converting from one method of expressing data into another. The ASCII code many people are familiar with, and you sort of think that's the standard one, but it's just an arbitrary one really. USB do it a different way, and as a result we kind of have to go through these slightly weird contorted translations between each one, but I'm just trying to explain them. You don't really need to worry about this code, you can just use it and it will work, but I'm trying to explain why it's here in case you ever need to add it or change it for a different device. And we go through the same thing again, so we've got the symbols on the keyboard and also the symbols on the keypad. The keyboard symbols are different depending on whether the shift key is being held. The keypad symbols have their own dedicated key to get those, so you don't need to check whether shift is pressed at the same time. We've also got the keypad numbers, and we've also got the special case of the spacebar key, which is down at the bottom, and that is denoted by the hexadecimal value to 0. So all of this function here gives a character value back, which is stored in last char, and we then print that value to the serial monitor, and we also write that value to the display. And again, like I say, if you're using a different sort of display from me, you'd need to call the appropriate method to write that value to your LCD or to your LED display, whatever you're using to display the output. Also, just mention, I'm only storing the last character value because I'm using that to determine when a string has ended. But you could, if you wanted to, store the entire string up to that value, and that's how you'd then implement some logic to say, if the players have scanned this code, then make this action happen, or if they've scanned this other product, make this happen instead. I'm just storing the last character value, and we're replacing that with each new item received. But if you wanted to, you could make this an array and store the entire string received. I'm just streaming it 1 byte at a time, or 1 character at a time, sorry, and then printing them as they arrive. Now the good news is, having done all that work in the parser, there's actually very little to do in the rest of the code. What we do in the setup function is we initialize a serial interface. This is just used for debugging and to check the values received when we call these serial.print commands up here. We initialize the display. Again, this is all specific to the particular display I'm using, but I just put up a little initial message just to say scan any item to begin. You can put whatever you want there instead. We initialize the USB host interface by calling the init method on the USB object, and we check that the returned value is anything other than -1. If it's -1, that means that an error has been detected, and so we'll print a message to the screen. But in any other case, the USB host has been initialized successfully, so we can carry on. We assign the parser that we just defined, so all of that complicated logic we were looking at a second ago, this is contained in a method in the barcode parser, and this was the parse method here, and this was the instance of the barcode parser class. So what we now have to do is attach that parser to the HID device, so that when any data is received from this device, we are going to pass it straight through to this parser. And this is, as I mentioned, you can have multiple devices. If you use a USB hub, you can have multiple USB HID devices, and you could define them here and pass incoming data to different parsers depending on which device it came from. But that is where it starts to get a little bit more complex. Certainly debugging it becomes much harder, as I discovered myself this last week. So I would recommend against it, if I'm totally honest. Stick with a single device and a single parser that will deal with all of the incoming data from that device. And then the loop function, well, this is super easy, because all we do is we call the task method of the USB class, and that will handle all of the logic for us, all of the polling the device, receiving the incoming data, calling the parser method as appropriate, and then all of the callbacks from the parser method will actually update the screen for us when new data is available, so we don't have to worry about it. So that's it. So hopefully that's explained the hardware and the software I used to take data from a USB barcode reader and get it into an Arduino sketch, from which you could use as the basis for an escape room puzzle or any other kind of interaction. I think it's a fun interface to use that players will enjoy. Now, if you wanted to use a different USB device instead, like a mouse, a trackball, a keyboard, or a Magstripe reader, the primary change you'd have to make is in the code to that report parser function, so that it instead looked at the items of data and the report format that was sent by the device. And the way to know what items to look for is to consult that USB specification document I mentioned earlier. I'll put a link to that in the description below as well. Now there are some other examples that come with the USB host library, and I've made some of my own variations for various escape room examples. I'll put a link to them also in my Patreon account, where I'll also upload all of the wiring diagrams and other resources and links to the products I used. So if you're interested in finding out more information, do please head over there and check that out. There's just a couple of other final points to note. I've been using an Arduino Uno simply because it had that convenient USB host shield that slotted onto it. And even though Unos are now relatively old technology, they're about 12-15 years old I think, they're still very robust and reliable and very useful for a wide variety of simple microcontroller projects. Now there are other boards you could consider, and the latest variant of the ESP32, I think it's the S3 version, does have USB host functionality built onto the chip. But it still doesn't actually have the hardware sockets, the USB Type A sockets available on most boards. And I don't think the functionality is actually officially supported in the ESP libraries either. So you'd still have to add additional hardware to use it, and you'd also kind of be on your own figuring out how to. So good luck with that. You could also use a Raspberry Pi instead, for example, but that's obviously totally different architecture and it's much more similar to using a mini PC. I wanted an example that had a simple, cheap microprocessor, and hopefully I've been able to do that to you. If you have any questions or comments or suggestions, or if you've got some ideas of escape room puzzles that could use USB HID hardware as a fun player interaction, I'd love to hear them, so do please write them in the comments below. I'll do my best to read them all and get back to you. And otherwise, I just want to say thanks very much for watching, and I look forward to seeing you next time. Okay, cheers, bye.